S-Chan presents educational video lectures as per the AICTE curriculum. Difficult concepts made easy. Study anywhere, anytime.
Have you ever wondered that a planar molecule such as cyclohexane, which appears to be planar, is actually not planar? We will discuss about this in our lectures. I'm Dr. Manika, and today we will be talking about stereoisomers. For more information on such topics such as stereochemistry, reaction mechanisms, you can follow our book by S-Chan Publishing, the link to which is given in the description box below. In this part of our lecture, we will be talking about conformational isomers. In the first lecture, we have talked about configurational isomers and optical activity. In this, we'll be talking about conformational isomers. So just to give a brief review of the things which we have done previously, isomers were divided into conformational isomers and configurational isomers. So configurational isomers were the ones which could not be interconverted to each other by simply bond rotation, whereas conformational isomers are the ones which can be easily interconverted into each other through rotation of the single bond. So for example, if you think about a molecule of ethane, what do you see? You see two carbon atoms which are connected to each other by a single bond. So here you can see that there are two carbon atoms which are connected to each other by a single bond, and each of them have similar atoms attached to each other, that is 6 hydrogen atoms. So a molecule like this can be expected to show isomerism. Yes. Why? Because this bond between the two carbon atom can be easily rotated, and because of this rotation, it exists in the various forms. This molecule exists in the various forms which are known as conformers or conformations, and these conformers or conformations exist in equilibrium with each other at room temperature. So these conformers or conformations differ from each other in their stability, and they exist in equilibrium with each other at room temperature. The most predominant form will be the one which will be the most stable form. So for example, as I just said, ethane, for example, can also exist in the various forms such as eclipsed and staggered form. So for example, we can see on the screen over here eclipsed, anti and gauche conformations of butane. These are shown to be in the Newman projection. Newman projection are a way of representing conformational isomers where each carbon atom is represented by a center followed by another circle which represents the second carbon atom which is connected through the single bond. So every aliphatic molecule or a cyclic molecule which happens to show conformational isomer can be represented in two ways, Newman and sawhorse projection. Why Newman? Because it just look like, if you look at the Newman projections over here on the screen for ethane molecule, it looks like the face of a man. So that is why Newman. And the sawhorse look like someone is riding over a horse. So that is just to remember it, a way to remember it. So you can see through the Newman projection, if this is marked as C1 of ethane and the circle is marked as C2 of ethane, then this center is connected to the carbon through a single bond, while the hydrogens on the C1 are in plane and the hydrogen on the C2 are just behind the hydrogens of the C1. So there must be a major interaction between the hydrogens in this particular formation, and if you rotate the similar molecule, if rotate this conformer by 60 degrees, then you just keep the C1 as fixed and rotate the second carbon atom by 60 degree, then you can see that there is minimum interaction between the hydrogens on the C1 and C2. Similarly, Newman can also be converted to sawhorse, or sawhorse can be converted to Newman. Both of these projections are interconvertible. In the sawhorse projection, the lower carbon atom is represented as C1 This is C1 and this will be C2, and both of them are interconvertible through bond rotation. That is the basic classification of conformational isomers or conformations. Conformational isomers are not expected to be optically active all the time. It's just that they represent the different conformations being possible via rotation through a single bond. Now let's look at the conformers of ethane. So again, coming back to the 3D molecule, here you can see that the two hydrogens which are above the plane C1 and C2 are eclipsing, that is, they are in front of each other. So this conformation is the most strained conformation, or this one is the eclipsed conformation, right? Because they have the maximum van der Waals interaction of these two eclipsing hydrogens. Such a strain is known as torsional. Such a strain which exists in the eclipsed conformation is known as torsional strain. So here you can see the two conformations of ethane. The one which hydrogens as possible farthest away from each other is known as the staggered conformation, whereas the other one is anti, or you can say eclipsed conformation. In the eclipsed conformation, the hydrogen at the adjacent carbon atoms are eclipsing with each other, and the kind of strain which they experience is termed as a kind of torsional strain, right? So when the molecule of ethane conformer, or when the conformer of ethane changes itself from the eclipse to the staggered conformation, it attains maximum stability. Therefore, in the energy diagram over here, you can see that the staggered conformation is at the minima, energy minima, while eclipse is at the maxima. The staggered one is more stable from the eclipsed by some 12 kilojoules per mole. So that's quite a substantial amount. Similarly, we can draw the conformations of aliphatic molecules such as butane. So here you can see in the energy minima, lots of conformers are being shown. So how are they getting possible? So looking at the structure of butane through the Newman formation, we can see that the two methyl groups are present on the different carbon atoms. The first carbon atom over here, has CH3, while the second one has CH3 opposite to it. I will just show this in the 3D representation also. So we can explain the conformations of butane through a 3D diagram also. So look at the molecule of butane over here. Here the orange balls represent the methyl group. So when these methyl groups are farthest away from each other, this is the most stable, or the anti-conformation, or the staggered conformation. So here there is no torsional strain in the molecule, and now when we rotate the molecule just by 60 degree, the CH3 and H are eclipsing at two positions, right? So this is a kind of eclipsed conformation and is relatively less stable than the anti one. So again we try to make a rotation of 60 degree. So when we make another rotation of 60 degree, both the CH3s are at an angle to each other, but they are not eclipsing. Since they are not eclipsing, they are adjacent to each other. This is a kind of gauche interaction, and this gauche interaction is known as Gauche-butane interaction. Since it exists in the butane, this interaction is gauche. So this interaction, which is obtained by a rotation of 60 degrees, is known as Gauche-butane interaction because of the CH3 groups being present adjacent to each other. So when we make another rotation of 60 degree, what happens? CH3 and CH3 are completely eclipsing. So this has the maximum torsional strain. So this conformation has the maximum energy barrier. So this is known as the eclipsed conformation. This is another eclipsed conformation, but relatively more unstable than the eclipsing with the eclipsing of CH3 and hydrogen atom. Again rotate the molecule through 60 degrees. So whatever rotations we are making, we are keeping the C1 as fixed and we are rotating the C2, that is the carbon atom, behind in the Newman projection. So again we get the Gauche-butane interaction where CH3 and CH3 are adjacent to each other. And the last conformation which could be possible is another eclipsed conformation. So if you rotate it another 60 degree, you will get again back the anti. So the same energy pattern will be repeated. So the different conformers are possible for various aliphatic compounds like propane, butane, ethane, and they explain us the phenomenon of reaction mechanism. So why are we actually studying these conformers? Because the molecule is not going to show you any optical activity, but when it tends to react with olefins or alkynes, or it undergoes some sort of substitution reactions, then it becomes quite easy to understand the stereochemistry of the reaction mechanisms in those cases. So now in the cyclic systems, we have more than 5 or 6 membered ring systems, or even less or even higher. It's not restricted to just C5 and C6 which we usually encountered. C3 also exists, C4 also exists, C5, C6, so on and so forth. Annulenes which have C10, C12, so on and so forth. Crown ethers, cryptins are there. So in most of these cyclic systems, whenever the ring size goes beyond the 5 or beyond or less than 5 or 6, the molecule has some sort of instability because of the angle strain. So we have studied 2 types of strains till now in our conformations, angle strain, torsional strain, and Gauche-butane interaction. So these are the 3 basic type of strains which exists in the conformational isomers. So as and when the size of the ring increases beyond 5 or 6, or it goes down 5 or 6, the carbon atom gets strained. Look at the molecule of cyclopropane. We know that the carbon, whenever it is present in the tetrahedral state, bears the bond angle of 109.8 degrees. But when it is in the cyclopropane, you can see how much strained it is. Here the bond angle is around 60 degree and the additional angle of 49 degree is still to be balanced out. So the ring is quite strained. So this one has got a maximum angle strain. When we move to cyclobutane, this has a bond angle of 90 degree and again we have to encounter say 19 degrees of stabilization. So there is also some angle strain in this molecule. When we move to cyclopentane, when we look at the molecule of cyclopentane, it has an internal angle of 108 degrees. So this one is just, so when we look at the molecule of cyclopentane, this is close to the tetrahedral angle and obviously the angle strain reduces. And when we finally look at the molecule of cyclohexane, the internal bond angle is 109 degrees, which is close to the tetrahedral. So this cyclohexane is mostly free of the torsional strain or any sort of the angle strain because it undergoes some sort of puckering. Unless and until the ring system undergoes some sort of puckering, it will always have some sort of the angle strain. So cyclohexane molecule exists in the puckered state. Puckered state. Puckered means twisting. So as the ring size increases, the molecules tends to undergo puckering in order to get rid of some of the angle strain. And in the case of cyclohexane, the most stable conformation is the chair conformation. So cyclohexane exists in the most stable conformation, which is the chair conformation. It is the puckered conformation. If you look at it, if you think about it like in a 3D form, it is just like a chair with this sort of orientation, puckering at both the ends, pointed at both the ends, and a flat surface for like the sitting. That is how the chair looks like. So this is also the energy diagram for the strain with respect to the ring size. Here you can see that the carbon atom, the ring system with the 6 carbon atom will have no strain. It was devoid of any strain because the molecule undergoes puckering and the bond angle is also tetrahedral bond angle. Below this, there is some strain. Beyond this, again there is some strain, and as the molecule undergoes puckering, it kind of tends to relieve its angular strain. The most basic molecule which we study in the organic chemistry to study the conformations of cyclic system is of the cyclohexane, because it is easier to understand and it is the basic structure which will help us in understanding about the orientation of the atoms attached to a 6-membered cyclic system. So cyclohexane ring has a 0 angle strain and torsional strain. This is how the chair conformation is represented. Here you can see on the screen there are 2 types of the bonds, red bonds and the blue bonds. The red bonds are termed as the axial bonds. The red bonds are the axial bonds. The blue ones are the equatorial bonds. So if you look at the molecule of cyclohexane in the 3D representation, just try to imagine it out. The red bonds are represented as axial bonds and the blue ones are equatorial bonds. So all the axial bonds are up the plane of the paper or down the plane of the paper, whereas the blue bonds are inside the plane of the paper or outside the plane of the paper. So as to say that axial bonds are in the plane of the paper, while the equatorial bonds are inside or outside the plane of the paper. So here you can see on the C1, the axial bond is above the plane of the paper. The C2 axial bond is down. C3 axial is up. C4 the axial is down. C5 axial is up. C6 axial is down the plane of the paper. Now look at the equatorial bonds. The equatorial bond at the C1 is down inside the plane of the paper. C2 equatorial outside the plane of the paper. C3 equatorial again inside the plane of the paper. C4 equatorial is outside the plane of the paper. C5 equatorial is outside the plane of the paper, and C6 equatorial is inside. So axial and equatorial bonds are oriented alternatively so as to minimize any sort of torsional strain or eclipsing interactions. If you look at the structures of substituted cyclohexanes, you will be able to draw the most stable conformer depending upon their position with respect to the axial and equatorial bonds. Let's look at the conformations of the cyclohexane. The most stable conformation is chair conformation. So if we twist this chair by some amount, we get a half chair conformation, which is the least stable of all the cyclohexane conformers. And if you twist half chair by a further amount, we get a twist boat conformation, which is relatively less stable than the chair conformer. Twist boat, if twisted further, gives rise to boat conformation, which is another unstable conformer but less stable as compared to the half chair conformer. Again, twisting the boat gives us twist boat followed by half chair, and again we get the chair conformation. So all the conformations of the cyclohexane are obtained by twisting the chair conformer, which is the most stable conformation of all of them. And most of the reactions in organic chemistry or their stereochemistry is understood by taking into consideration the chair conformation. So that is the most important of all. So just a brainstorming question. If you look at the structure of cyclohexane trans 1,2-dimethyl or 1,2-dimethyl cyclohexane in its trans form, what do you expect the methyl groups would be oriented as? Both axial, one axial and one equatorial, or both equatorial? So keep thinking. The answer to this question will be disclosed in the part 2 of the lecture. With this, we come to the end of the part 1 of our stereochemistry lecture of conformational isomers, where we have talked about the various conformations in stereochemistry, conformations of ethane, butane, cyclohexane and its various conformations. I hope you liked the lecture, and we will be talking more about the stereochemistry in the part 2. So keep watching. For more information on such topics such as stereochemistry, reaction mechanisms, you can follow our book by S. Chand Publishing, the link to which is given in the description box below. Please keep liking, subscribing and sharing our channel for more such videos. Thank you.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.